Hello folks, we are going to prove the point of concurrency for the 5 lines from the previous question. We're going to first assume that it exists, as you can see on the figure, and we are going to also assume that its position vector is represented by p bar, and we're going to use the centroid and the perpendicular relationship with the sides of the pentagon to show that P in fact exists and what its position vector is going to be. So assuming the point of concurrency exists, right, we will then proceed to show that its position vector is similar for all all 5 lines. So the first thing we are going to do is represent the vertices by position vectors A, B, C, D, and E. And assuming the centroid of the triangle ABC is A plus B plus C over 3, we call that ℓABC. And then we represent the line DE as the position vector D minus E, right? Because that would represent the vector or the line going through DE. So D minus E could be the vector representing that. And the relationship between the vector or the line DE and the line going from P to G is that they are perpendicular, as it is already given by the question. So if you dot those two, you should get a 0, which is important to note. But then if you were to rotate D plus E by 90 degrees, then that would mean P minus G becomes parallel to D plus E. And so that's why we're going to do rotated, and then remember that V minus U is a rotation by pi over 2 of V plus U. So D plus E is 90-degree rotation of D plus E. So D minus E and D plus E are 90 degrees apart, rotated. So then that means P minus G and D plus E are then parallel to each other, and one can be written as a multiple of the other, right? Two parallel vectors are either similar in quantity, or one is bigger and the other is smaller, or their direction is different, right? Like, so those are the 3 things it could be. But n could all encapsulate all that information. So P minus G, n1 times D plus E is our discovery. And then the G is for the triangle ABC, which from your class is A plus B plus C over 3. And if you solve for that point, the position vector P for the point of concurrency, it ends up being A plus B plus C over 3 plus n1 times D plus E. Okay, so that's good. Let's just repeat the process for the triangle BCD, right? P minus the centroid for the triangle BCD is parallel with the 90-degree rotation of the line segment EA, right? So EA and PG, right, are perpendicular, but if you were to rotate the EA vector by 90 degrees, it then becomes parallel to P minus GBCD. That's what we're going to do here again, right? So that ends up becoming, as you can see, B plus C plus D over 3, which is equal to N2 times E plus A. And our position vector P will have to be represented by B plus C plus D over 3 plus N2 times E plus A. Now, we were first assuming, that position vector P represented a single point, meaning there is a point of concurrency for all 5 lines. But now we're actually showing it. So the first 2, as you can see, the first 2 points of possible concurrency are these 2 represented by asterisk 1 and 2. So for these 2 to be equal means there is a point of concurrency, and that can only happen when n1 and n2 are equal to each other, as I will show you in the next page. But so how do we actually show that it is 1 over 3? Well, assuming P for ℓABC is equal to the P for ℓBCD, we then set the expressions we found previously in the asterisk equal to each other and solve for n1 and n2. And so second step here is bringing this BCD plus 3 term to the left, which would make it negative. And you take the n1 times D plus E term to the right, should make it minus n1 times d plus e. And then the BC cancels the BC here because of the sign, and you end up with a minus d over 3, which will have to equal n2 times e, n2 times a, minus n1 times d, minus n1 times e, if a point of concurrency was to be found for ℓABC and ℓBCD, right? And so here we're just going to do some more algebra to preserve the a minus d term on the right and get rid of the e because we don't have an e on the right, on the left. Then n2 minus times e and n1 times e will have to cancel each other out, and that can only happen if n1 and n2 are equal to each other. So you do that and simplify to find this, and now n1 clearly has to be 1/3 because that's the only way these two terms will equal each other. So again, n1 is also equal to n2, which is why I didn't use n2 here. You could just say n1 for all of them. Great, right? So we found a point of concurrency for the first lines, ℓABC and ℓBCD, which are lines that go through their respective triangles centroid and are perpendicular to, and those lines are also perpendicular to the corresponding side of the pentagon, which is DE for ABC and EA for ℓBCD. After that, it's just repeating the same process. You do the same thing for triangle CDE. You solve for the possible point of position vector point of concurrency, and then you see that for this to be concurrent with the corresponding two lines, or the previous two lines, n3 would have to be 1/3. Same thing with DEA, for the position vector to be equal to the position vectors we found previously, which also means there's a point, the point of concurrency is similar, right, is 1/3. So you show that n4 equaling 1/3 gives us a point of concurrency for the line ℓDEA. And finally for ℓEAB, you solve for it and you see that the n5 term will have to be 1/3 for it to be that 1 point. So all the p's we found for all 5 lines are pointing to one single point, P, which is the point of concurrency for all 5 lines. And so in this whole process, what we did is we showed that the point of concurrency P exists, and that its position vector is A plus B plus C plus D plus E over 3. And so that would be your solution. But yeah, let me know if you have any questions, and I'll see you next time. All right, bye.